Thank you.
Welcome to RISE Learning Machines seminars. I'm Olof Mogren, and I'm a researcher here at RISE on machine learning. RISE is Sweden's public research institute, and this is our weekly seminar on AI and machine learning. The meeting will be recorded, and if anyone wants to be removed from this recording, just let us know afterwards by dropping us an email. Also, check out our collection of great talks, which are recorded on our YouTube channel. Today, I have the pleasure to introduce Oskar Täckström, who is Chief Scientist at Sana Labs. Oskar obtained his PhD from Uppsala University in 2013, and his publications won Best Paper Award and Test of Time Awards at NACL 2013 and ACL 2023. His research interests include attention-based models for language and video generation, deep learning for mRNA molecule design, and he's been previously been senior research scientist at Google. His current position is at Sana Labs, as I mentioned. This is a company aiming to advance how humans access knowledge with AI. And the topic today, as you can see on the screen, is from enterprise search to intelligent agents. And with this said, I will stop my screen sharing and hand over the stage to you, Oskar.
Thank you. I'll send a request for taking over the screen now. We'll see if that works.
Yes, good.
Yeah, thanks for having me. Thanks for the introduction. This talk will be about the work we do at Sana. It's going to be a mix of, I guess, a bit more high-level industry commercial talk, but also diving into some what I find is very interesting research going on right now, and how we use these things at Sana. So I only have one screen, and that's devoted to the presentation now. So if you have, just raise your voice, I guess, if you want to ask something in the middle. Because I can't see you now.
Is Oskar's screen showing for everyone?
No.
Oh, it's not. Okay. No. It should be a, let's see how I can make that work then. Now, you see something green.
Yes, looking good.
Thank you. So yes, it will be a mix of a bit of high-level thing, and then also going into some details. And if you want to spend more time on a certain thing, just let me know, and we can do that. But just first a bit about Sana. We're a company based here in Stockholm. We have offices in New York and London as well, but we are have all our technical development going on in Stockholm. Our mission is basically to accelerate knowledge in order to accelerate everything else. And to that end, we're focusing on building a world-leading enterprise AGI lab in Sweden. We have investors like EQT, NEA, Menlo, and Workday. We raised $130 million, and we work with some of the biggest companies in the world. And what the problem we're solving for these companies is removing the complexity of building enterprise AI applications. So in order to accelerate knowledge in big enterprises, you need to integrate and make sure that all knowledge that is spread out across the organization is available, ideally in a single place. So we have built connectors to hundreds of third-party apps. We then provide access to all the information and knowledge stored in those apps. That could be databases, graph databases, SQL databases, free text documents, also apps like Salesforce and so on. And then we respect all the permissions at the source, and then provide an interface for searching and interacting with all of that knowledge, and also taking actions in those apps. So companies plug in their integrations, and then they can build with simple kind of no-code solutions, build on top of that assistance, search, and also agents. So with this, you can seamlessly connect search and assistance and agents, all your knowledge and data, as I mentioned. And we also have so that you can record meetings and get meeting transcripts, and also basically record everything that's going on and have that merged with the rest of the knowledge. And the key value of all of this is that you get a synergy between all the knowledge in the company, so that you can basically, if you're in a customer support, you can, get not only you can have access to all the questions and issues that customers come to you with, and then you can also very easily join that automatically with all your product information data and all other relevant data in order to then accelerate how customer support agents work there. And then you can apply this to any different function in the company. So that's kind of a very high level of what we do. This talk, I was planning to talk about what I call the 3 arcs of enterprise AI. So this is basically kind of the transition from enterprise search through assistance. So search, finding data, knowledge, and people in the organization, to assistance where you can get answers to reasonably simple questions, analyze data of limited complexity, and also generate content. And then all the way to agents that can execute multi-step workflows, take actions, also run in the background in order to proactively serve and suggest actions and decisions and use tools. So I will start with search, and I will spend most time on search when it comes to, I guess, the more traditional academic deep dive. Then it will be a bit more high level. But if you want to go deeper on some topic along the way, you should stop me. So with search, we now have this. We integrate to all company apps. So basically, you can then search from one interface all the information available across those apps. And what I want to highlight here is how enterprise search is being transformed. So enterprise search didn't used to work. And it didn't really work for, I think, 3 main reasons. One was that to understand the content of documents, like in enterprise, you have such a vast diversity of how content looks. You can have slides with very important information buried inside a slide deck. You can have them in PDFs with charts and tables and so on. You can have them on things with very strange layouts and so on. And also you can have just, the data stored in databases and so on. And you want to basically be able to search and join all of this through one common kind of abstraction. And that really didn't work. So for documents, for like PDF documents, what people used to do is you had these pipelines of OCR. Maybe you had, if you were fancy, you did some table detection and tried to then run a table extraction model on that. And then you had like an image extractor detector model, and you tried to like run these very simple models and piece together the pieces into something that looks like text. What's happening now is that we're just basically taking screenshots of stuff and using multimodal LLMs to handle that. Similarly for the ranking, so that's just like the ingestion, right? To being able to understand even the content of the documents. Then the second one is you used to need massive amounts of click data to be able to do any kind of search, because you needed to fine tune. Either if you use just a free like text search, you had to basically associate terms in the query statistically with terms in the documents, and to do that properly, you needed like a lot of click data. Or massive amounts of label data, which is extremely costly to produce. So no one did that. What's happening now is that instead of relying on click data to try to understand and associate query words with document terms, we again use language models to understand and reason about both the query, the context which the query was written in. So that could be like your whole history with the system, and what's happening in the documents. And then finally, and one thing that people did beyond this, click data is you use that click data basically to also fit different types of scores. So you might have like a recency boost scorer. You might have some other scorer based on popularity. You might have like basically usually you would have maybe up to 10 different scorers that you then try to fine tune. Now we're also seeing that some of this, at least this is a bit more speculative. We're just basically getting started on this, but preliminary experiments suggest that we can use language instructions to instruct the systems to do this kind of in a very zero-shot or few-shot approach. So I will dive into each of these and see point to some recent research that we based this on. So for the OCR plus detection plus parsing, here's just an example of taking a recent paper called GrantGPT, screenshotting the different figures in the paper, and then asking, in this case, GPT-4o, which is the best retriever, what's the second best performance on, and this, just by looking at the images, these models flawlessly answer the question. So this means that these models can understand content that is in figures and charts. You don't need to first extract that as text and then pass the text to the model. So this is like, this means that we can use, we don't need to actually do these steps, but we can go directly from the visual content. Also, in a lot of these cases, to understand really and derive conclusions from a graph, it's not enough to just extract it as text. You need to understand, colors. There might be certain things in the graph that is highlighted or larger in size, and it's like positioned relative to something else. And that is what conveys the actual, like a big part of the meaning. So it's actually easier in a lot of cases for these models to reason from the actual graphics rather than a description of it. So one paper here that I think is really cool is this recent paper on called Pali. So there they show on this academic benchmark that if you do just a screenshot of the PDF page, you can replace all of the OCR layout detection and so on. It's much, much faster to do that. So instead of 7 seconds per page in total for that pipeline, you spend like 400 milliseconds on it. And then in the retrieval phase, it's actually comparable latency to query the full multimodal content rather than just the text. So you don't really lose anything at search time either. So it's a big win. And then if you look at the score here, so with the standard retrieval, that when you first run OCR, you get a text representation. You then take a text embedding model. If you replace that part here now with this vision encoder that extracts just both text and like the screenshot here includes both the images in the PDF, right, and the text. And then you can go from like 66% NDCG at 5 to 81% NDCG at 5, which is a pretty dramatic improvement. I won't go into too much detail on exactly how it works. Basically, it breaks the PDF into patches, and then you embed each patch separately and you embed them in a way which is easy to binarize. So you can make these very small sparse vectors, a collection of sparse vectors to represent the image content, and then you take this max sim operator. So basically, each token in the query will be matched against each possible patch in the image, and then you take like sum those up so that you get a max similarity across all the query terms. So okay, this is cool, but what's happening now, and which is like, I think this is why we are betting on all of this, is that if you look at this paper came out earlier this year. Now, by just switching out the VLM model from this PalyJamma model to a model called Qwen, which is the only change you do. Now you go from 85% on this NDCG metric upwards of 90%. So this means like whenever a new VLM model comes out, we get better retrieval. So we get that for free basically. And these models come out every 3 months at least. There's some new development. So this is really, really cool. Then another, so you could use this called Pali, where you split up the PDF into patches and you do this max sim operation where for each query token you look at the maximum similar patch. But you could also take just a screenshot of the page and some patches and then directly feed that into an autoregressive language model, and then do the same with the query, and then you can compare them. And this is another approach, and it works similarly well. So even with content that is just text, you lose a slight amount of quality compared to if you had those documents represented as pure text. On the other hand, you can now handle any type of content in the same way. And on content that has a lot of images in it, or visual content like slides, now you see a dramatic improvement. And I think if you just follow the trends, it's pretty clear to me that the image-based models will very likely be on par with the text models. I don't see a reason for them being much different. Okay, so that's very promising. So we can use basically one single retrieval model across all types of content, basically. On this slide, it was a bit old. This shouldn't have been there, sorry. So one thing that is really, okay, it's cool with these academic benchmark results, but when you work on enterprise data, the problem is that a lot of models start to pretty quickly overfit to the content of those academic data sets, which is not necessarily reflective of the full diversity you see in the enterprise. So one very recent and encouraging result here is that you can do now zero-shot ranking. So you can do initial retrieval with this model, but then you can re-rank the results, and you can do that zero-shot. That means you have a large language model like GPT-4 or GPT-4o if you also have visual content. And then you basically just prompt it to do a ranking. So you put in the user query, and then without any further fine-tuning on the retrieval task itself, you can get superior performance based compared to the state-of-the-art re-ranker model. So this is really good because when this works without any fine-tuning, you have a much higher probability of translating to very good results also in an enterprise context. So any kind of unsupervised result is, to me, 10 times stronger than any kind of improvement on the academic data sets, only when you actually do fine-tune on those tasks. Another thing here with ranking in this context is this previous slide showed that, so here you have the blue one here is this Mono T5 3B re-ranker model. And then you have GPT-4 here as the zero-shot ranking model. But this is on a data set similar to which that supervised ranker in the blue was actually fine-tuned on. And if you look at supervised re-rankers, so those are basically models typically that are point-wise re-rankers. So you take, you use BM25 or you used some text embedding model to first do a first pass ranking, and then you re-rank those results. And you do that basically by looking at the query and each document separately, and you give a score to each document and query pair. The problem with that is that, and that was shown in this paper, Drowning in Documents, the consequences of scaling your ranker inferences, they kind of work when you have a small number of documents in the top results. So they are pretty good at re-ranking the top 100 maybe results. But then if you add more results, they actually perform worse than the embeddings using a good embedding alone. And this is because these supervised re-rankers are trained in such a way that you give it like, you take a query and you take a good document and then you sample a smaller set of bad documents and you have a contrastive loss. What happens there is these models typically don't see a lot, like they only see a subset of the good and bad bad documents. And then once you have documents in there that are not seen before or unlikely to have shown up in that dataset, you basically get out of distribution and you get any kind of weird scores from these re-rankers. So this is even more encouraging, right? That this LLM-based ranking beats all supervised re-rankers, and they do it on the data sets where the supervised re-rankers are likely to actually work, but then in practice they often fail when you go out of that scenario. So that's an even stronger indication of this. Okay, but using something like GPT-4o or like kind of a very large language model for ranking on it at test time seems very costly, and it is. What you can do then is And this is also something that is extremely relevant to the enterprise context, where you might have different customers that have very different kinds of data. So what you want there is you want a recipe to be able to create fast models that actually work well for their kinds of data. And to do this, you can use this heavy zero-shot based approach, which is generalizing really well to different scenarios, but slow. And then you can distill that on data that looks like the data that your customer have. So you can then, you have like a recipe now where you take slow models, but really good ones. And then you basically turn the crank and distill them into good models that are small. And this is kind of the recipe that is needed. So the whole approach we take with all of this is, instead of starting with a small model and try to make it work, we start with like the thing that works, and then we work backwards and we distill that into something that is fast. Because it's really hard to go the other direction. Otherwise, then you need a lot of data, fine-tuning data that you need to create yourself. So relying on kind of synthetic data and distillation methods is really what works in the setting. And then if you use something like LoRa fine-tuning on the smaller models, you can share the backbone, so you can have different customers share one part of the model, and then every customer has their own specialized module on top, which also makes it practically servable. Okay, so finally, this is more about going from twiddlers and scorers to language instructions. So what we see here is that by having different parts of the organization just explain how they access their data and what their conventions are for storing it, we can, when we use this zero-shot LLM-based approach, since that also can take instructions and adapt its understanding based on those instructions, we can have humans just basically instruct the models how data is stored in their part of the organization and how they prefer rankings to look like. And that could even be on a user level. For example, you can, as a user, then correct the model when you see it's giving you the wrong types of documents. And even you could even take click data and then create synthetic kind of data based on that you then pass as instructions. So in this case, if I had these instructions, if I search for action items from Sun AI stand-up since Christmas, I would get like a date filter with all the meetings since Christmas, but I would get, in this case, a filter looking primarily in the Notion integration, because I just stated up here that we have our stand-up meetings there. So this is like a no code configuration for different parts of the organization, where anyone working there can kind of tweak the system without knowing anything about ranking or twiddlers or scores or anything. So that's pretty cool, I think. Okay, so that was the kind of deep dive into search, and I spent most time there a bit more in depth because I hadn't looked at the information retrieval in a while, and then when I started looking at it earlier this year, I was kind of blown away by the fact that suddenly really cool stuff happened in that field. It seemed like we got BM25 and then we got 10 different variations of it that didn't really push things forward. And now in the last 2 years, so much things have had happened in that field. So I was just very excited about it. And wanted to share some of that. But for the second part, I will go into a bit more about how we think about this assistance, what happens to the interfaces now, when we have these kinds of retrieval backbone that can actually find the relevant data across all the company knowledge. What do we do with it? So this is about creating these assistants where for every team, you can configure your own assistants. And you can configure them by setting filters of where to look. You can upload custom documents. You can provide these natural language instructions on how they should use and respond, where they should look and how they should respond to the user. And this is all powered then by this Retrieval-Augmented Generation. So in addition to this whole underlying retrieval backbone, which is powering everything, we also have this query planner or query agent. So you could have a user ask an assistant something. For example, you could ask it, you know, what's the status of this project? How is this customer relationship going? What happened since we last met with this customer? And this query agent will basically read the task description of the user or the query, and then use this assistant configuration and basically create and write queries to the underlying retrieval system. And this could be a single step thing, or like it could do a single search, or it could break down the user input into many different searches that needs to be done so that you can get information from different parts of the system and then combine it. So one thing we have here, we also have, as you see here, we have database search. So one example is customer support. You might have your product database encoded as a knowledge graph where you can do very precise filtering and find, for example, all the accessories that are compatible with a product with a certain dimension or torque or whatever. And then you can get a customer support email. Maybe that's in Zendesk, and the customer might ask something about what accessory should they add to this tool to support something. And then what you can do is, like, this query planner will go out and find the Zendesk ticket or email from the customer, figure out what, and then in parallel also look at the product database and write SQL queries or graph queries to that database, and then join that result. And the joining is just happening by basically sending everything to a generative LLM in the bottom. And with this framework, you can answer a lot of different questions and solve tasks for all parts of your organization. And this is just some case study numbers where we've seen with this kinds of assistant, you can get twice the number of support issues resolved. You can save up to 10 hours per week per employee, etc. Some of these are like, a lot of these are repetitive tasks where, for example, you have to, you know, customer support tickets, you get a lot of those, so that's very repetitive, and you do kind of similar things every time. Some other cases are more like one-off things. But all of these traditionally so far has been primarily done through a chat interface. So an assistant has, similar to ChatGPT, you have like a chat window and you ask a question, you get a response, and then you can iterate back and forth and so on. But we think really will unlock a lot of value in the enterprise context, especially when you have these recurring use cases, or, you know, what you want to do the same kind of task, but across a lot of different documents. We want to go beyond this chat UI. So we're building this Canvas interface where you can have an assistant that writes documents together with you. You can have a sheet functionality where you can parse input in the form of maybe a CSV file, or just create a query, and out of that query get a list of results, and then for each of those results perform run certain assistants to extract certain types of information from that. We're also having these schedules and workflows where, similar to what I showed, this query planner that takes input and writes basically search queries. We also have this version of it that can also not just create the search queries, but it can also predict tasks that should be performed. So this way, the user can set up, in this case, instruct this model or this assistant to set up a simple workflow where you can look at all the product feedback that came in since yesterday, summarize that, and send a message. So those are kind of simple workflows that can be powered by the same, and all of these are powered in by the same underlying building blocks, with just some things on top of it. Also here, now you can do this background task. So instead of just every time having to ask the system active yourself, you can, for example, before you enter a meeting with a customer, get basically have the system go out, this assistant be configured to go out and just summarize everything that happened since the last call with the customer, and bring that to your attention before the meeting. So these assistants are surprisingly good when they work, but they're also pretty underwhelming. So when they work, they can save a lot of time, and you get impressed by them. Now we have gotten used to them, I guess, so we are less and less impressed and more annoyed when they fail. But still, it's kind of this kind of jagged frontier indicates that tasks that we as humans think of as equally difficult, some of them these systems can handle really well, but some of them they fail. But as I said, when they work, you can save a lot of time. But what's happening now, and I wanted to spend the last part of this more on what I think is happening right now and coming, and what we are basically basing our assumptions on and building in to Sana. And this is the third arc, going from just this assistance that do this simple few-step workflows, and more towards agents. And I wanted to start here with what I think are the 3 ingredients to create intelligence, symbolized here by the 100 GPU from NVIDIA, test time compute in the middle, and then self-play at the end. And this will be a bit more speculative at the end, but I think it's very interesting. So what happened, just to summarize, what happened in the last five years or so? Basically, what happened was we just found the scaling laws, we brute forced our way and just pushed more compute and more data. And this is the figure from the GPT-3 paper, which I guess most people have read. But I think it's the most important figure probably in AI research from the last few decades. Because this is basically what drove everything else in the last 5 years. So what happened here was basically we discovered the transformer architecture. We discovered then that we can not just represent text in that kind of model. It can handle anything that we encode as a sequence, including images and videos and audio and even structured data in code. And by just getting more of that data and training for longer and with more compute, things got better. Still, what happens with these models is kind of that we reached a plateau, right? So sure, we can train on all the videos on the web now as well, and that will give us probably better multimodal capabilities and some world model, so to speak. But still, we are limited by the fact that at test time, we run these with basically one inference step. So we take like one or a few samples from the model and then hope it did well. This is quite unlike what humans do, right? Basically, we don't just usually, some of us, I mean, I sometimes do that as well, just spit out the first thing that comes to mind, but usually we kind of also have some reflection abilities, and we take our time and deliberate, and then we reach much better results. So this is what's happening now also with the test time compute. So this, I missed to put the references here, but this left figure is from a really nice tutorial by Sasha Rush on how, basically speculations on how OpenAI built their O1 model. So one of the approaches to build such a thing, so O1 is this model that it just doesn't just output one single answer in one go, but it produces a longer chain of thoughts and until it reaches the solution. And one way to do that is to have two models, right? You could have a verifier model that is trained to verify solutions, and then you could have a generator model which is trained to just output solutions. And then you can run either just beam search, sampling based approaches, or tree search or similar more complicated approaches. And then you can basically search for good solutions instead of just outputting one. And this has been shown, this dramatically improves results across a lot of different tasks like coding and math reasoning and so on. And this is from the O1 paper showing that when you do this, you get very similar scaling laws to when you do pre-training. So by just spending more time at test time or more compute at test time, you get better accuracy without changing anything else, and similar to pre-training. And there's a third version of this where you also see for retrieval. If you let the retrieval system look at more documents, then again, very similar, you get better and better hits. So by using more compute for retrieval, you also get better results. So then finally, this was, I thought, quite speculative when I gave this talk the first time a few months ago. But then things happened since, and I think it's now pretty conceivable. So, with systems like AlphaGo, for games, we saw, and when you could simulate the environment, then we can train these very superhuman models just by letting them play with themselves, basically. But that's kind of hinged on having an oracle that, the rules of the game that you follow, and then also having a well-defined and easily computable oracle that told you if one solution was better than the other. We don't really have that for human tasks, right? And we can't really get enough labeled data for human cognition. What's happening now, though, if you look at this test time compute approach, where you can train a model that is good at verifying solution and another one that is good at coming up with solutions, this starts to be a bit more conceivable. And what's happening now, just very recently, saw this paper the other day about multi-agent fine-tuning. So this is like what we used to call self-training. So back in the day, when I was doing more of the traditional NLP research, we did a lot of this self-training where you train a model and then you basically use this probability distribution from the model as a teacher to train another copy of the model. And you could kind of do this, but it was also very finicky. So you could only do like a few iterations of this before you started to kind of derail. But now with these kinds of models, it's turning out that with proper ensembling and so on, you can get models, even language models, to get better at reasoning and solving a lot of problems by just training on their own output. So I think this is basically setting the stage for basically overcoming the hurdles of the web. We're running out of data from the web and so on, and now we can start to be conceivable that we can get further improvements even if we plateau with both test time compute as well as pre-training compute. So why am I bringing up this? Because for an enterprise context, the real value that you can create is not really to just find the right document or to quickly find the Wi-Fi password. Those things, those are important, but really the really big value to unlock there, I think, is when you start having systems that can do quite complicated research and basically give you everything you need to make a good decision. This now starts to be possible when you have models that can look at their own output and reflect on it and come up with even better solutions. And now you're starting to get into the realm where we can actually have these agents that we can run in this way. But still, I would say right now, to make this work from our experience, is basically that you need to give these agents very kind of constrained tools, constrained environments, and constrained instructions. So you basically, for example, if you're creating this query planner agent that can perform searches and rewrite and find and also take actions, you need to think carefully and do a lot of feature engineering still on how what kinds of search tools are available. How do you represent a search filter? How do you represent the search results to the model so that it can do the ranking? Those are still kind of finicky, and we need to do a lot of feature engineering. But I do think these results point to a future where more and more of these things will be more or less zero shot doable. So yeah, just want to conclude with, I think the next decade will be quite different from the previous one. just as the previous one was quite different from the one before it. I think we will have these models that we can deploy in the enterprises to do quite complicated things for us. I think this will be really enable a lot of new things to happen in organizations. For example, in medicine development and so on, having these kinds of agents that can read all the scientific literature and draw conclusions from it, combine that with experiments performed in the organization, if you're in a biotech, and so on. And one other thing here was, of course, is that once you have one model like that works at this, then you can run many copies of it. So it's the only limiting factor is going to be, I guess, then energy consumption, and that is will probably become the determining factor in the end if you take this to the extreme. But I think still we're quite far from that, and we will see in the realms of what's possible and economically feasible. We will have tools that we can deploy at scale and really change how we work in the enterprise. Yeah, that's it. Let me know if you have any questions or thoughts or discussion topics.
Thank you, Oscar, for this exciting talk. Sounds like we're approaching a bright future.
I hope so.
Yeah. While everybody thinks of the perfect question to ask Oscar, I'd like to ask a question. You received your Test of Time award from ACL with a paper on parsing, I think multilingual parsing.
Yeah.
And now you're talking about sort of every 3 months you plug a new language model into your framework, and the scores improve. Would you say that sort of working with natural language processing has sort of stepped up in sort of the abstraction levels? Are you working more high level? Are you working more with sort of Lego blocks now than you were before? How has it changed for you?
I think it's changed completely, but it did already change completely for me. I think back in 2015 or something, when I worked at Google and tried to employ. So I started out with more academically, right, working on parsing and semantic parsing and other things like that, which was very fun, and still like the fundamental underlying building blocks are still very relevant. But I think those problems, as to use them as engineering tools, already in 2015, I realized that that was very tricky. So I was basically, back then what I was doing was taking a semantic parser that could look at, this was at Google, so this was like search queries. You could basically break them down and understand the different parts of the query and build relations, so kind of build like a DAG or RDF triples from it, and then use those triples to answer queries. The cool thing about that is that you could answer like multi-hop queries, and you could do joins and things. So you could convert it, basically the user query, to more or less like a soft, fuzzy database lookup kind of, where you could, say which movies did this actor, like which movies by this director did X actor also act in, things like that kind of. But then when I started to try to actually do it on real user queries, I realized that this is not how people, like language written by people, is just so diverse that those kind of abstractions broke down pretty quickly. And then the only solution I found was to basically use deep learning and very large data sets. So that was like I think from that on, this is the realm I've been operating in. And I think that's taken to the extreme now, even more. So I think a lot of people still have this mindset, which is based on how we used to have to do it, which is we trained one model per task. And at the time, there was this paper, I think this was also like 2015 or something. I think it was a paper by Richard Saucher, where you basically took all the different problems that people worked on in NLP, and you had, like, instead of having them as separate tasks, you basically described the task in text. You had the input, and then you had the output, and everything was text. And now I was like, at the time, that's pretty neat, but it felt a bit like I was still in the mode of like building specialized models for every task. But this is now what really powers everything, right? Basically, we just describe things, and you have this very versatile model that has a lot of common sense reasoning abilities that you then just dump in this in, and then you can prompt and like feature engineering and task-specific engineering that we used to do has now shifted to, you know, how do we represent the data to the model so that it's easy to make it easy for it to deduce what it has to deduce, basically. So I think the linguistic and that kind of background is still has been useful in the terms of also evaluation, like understanding how how to evaluate these things. And this is problematic, I think, how we do now in this field is people are training on the test sets all the time. So it's increasingly difficult to take at face value results, from these large language models on different tasks because the leakage of test set to training set is severe all over the place. And it's hard to get around it, right? Because when you train on the whole internet, how do you guarantee that you haven't seen that example already? But still, I think when you use these tools internally, you have to be disciplined and you have to know how to do these kind of things, right? Otherwise, you will fool yourself.
Yeah. Is it the joint many-task model that you're talking about from Sasha's group?
Yes, I think so. I kind of feels so long ago now, but it wasn't that long ago. Time has accelerated, I think, lately.
We have a question in the chat. Can distilling work on all the shown improved models, for example, after test time compute to save energy?
Yes, I think so. As long as you can find, and this is something we're exploring, like how do you, to fine tune these models, it's important that you fine tune them on data that is realistic, right? That looks like the data you will see in practice. So, but it seems like for a lot of tasks, you can get very good results by just having the state-of-the-art language models. Right, for example, if you want to do retrieval, look at specific data from a specific customer, write questions from about like grounded in that data, and so you basically generate synthetic queries, and then you can distill on that data. But the risk is that these models then generate questions that doesn't look like human questions, and there's evidence that shows that if you just run them and ask them to write queries, they will look quite different from what actual humans will do. So then you have to join that with like, how does people in this context actually express their search intent? So it's like you have to kind of look at, and that could be different for different organizations, right? If based on what domain they're in, based on what types of users they are. But then you can kind of, so you can do it in multiple stages, so to speak. So you basically have one model that learns how people write things in this context, and you apply that together with data from that context to generate realistic queries from that context. Then you can distill that. So that's kind of a recipe. Once you have that, there's no human, like we can't look at the data from our customers often. So that means that we have to have these recipes that we just apply, and then we just know that they will work. So that means also we can't do too much specialization, because then the risk of us overfitting to one particular scenario is too high. There's another hand raised.
Yeah, there's a hand raised from Thomas.
Yeah, hello. Thanks for the presentation. Very interesting. I was wondering, when companies are struggling with the sort of prompt engineering here, because it's hard whenever the large language models are changing beneath them all the time. Can you see the same problem here with the retrieval-augmented generation here, that one needs to re-index your data too often to keep up with the best RAG concepts?
Yeah, this is it costs quite a lot of money, right? And the more customer you have, if you want to re-index everything, it costs a lot of money. This is something we're actively thinking about how to work around. And I don't have a really good answer, but from what we're seeing now, I think the answer is to not do. It's very compelling or tempting to like prompt engineer the hell out of it, right? It's just like,
Yeah.
oh, you have a benchmark, you know, you change the prompt and it results go up. But you have to also think about then each time you do that, unless you change the test set every time, by doing this cycle, you're kind of starting to overfit a little bit. And so I think not overfitting, not doing too much prompt engineering, and trying to find other ways to constrain the system is probably useful. But I think the main issue with prompt engineering comes from when you try to prompt engineer smaller models, because then you tend to, the risk of overfitting to those is higher, I would say. Like the really big ones are less prone to that. And then if you rely on this distillation recipe, then it's not as big as a problem if they switch out. Then usually what you see is like if they have better capabilities, then the distilled models will also turn out better. Yeah, it is a concern to try to over engineer things too much and then risk overfitting.
Yeah, thanks.
We have another question in the chat. What are your thoughts on sensory or expert AI systems in more dedicated ways to improve resolution of user intent and circumstances?
Ooh, that was a long question. Sorry, I was a bit. What was the sensory?
What are your thoughts on sensory or expert AI systems in more dedicated ways to improve resolution of user intent and circumstances?
I don't know. I don't know what is a sensory. So expert system, you mean having kind of symbolic systems also that provide some constraints on the, or
perhaps David wants to unmute and ask this yourself. He writes also in the chat, as a way for the user to communicate with the AI resonating with the surrounding.
Yeah, so hello, and
hey.
very nice discussion. I was a bit late, but my question really regards whether if I have a sensor of, for example, temperature, then this can consist and make a different sort of AI system than use text as my input. This combination is still not present, from what I understand it, in a user-friendly way, but I think it will be integrated along in the future as very significant approaches. So, for example, you have this pattern or structure of computing your reasoning models over and over. But how do we dictate what the actual truth is, and given which circumstance? For example, you want a different rule depending on if the temperature is different, for example. So this is the question, like how do we see the evolution of input, really?
Yeah, that's a good question. I think not too sure about temperature, but I mean the simplest dimension beyond text is time.
Mm-hmm.
Right. So that is something we encode directly in this model. So you can, in the square planning module, we look at what time it is today and then what time all the results timestamps those had. And then you can have also other timestamps. So we know last edited and so on. And those timestamps you can encode those as text and the model can reason about it. I think if you do something with other types of attributes, they could be encoded in similar ways, I would assume. As long as there's some kind of, I mean, either you have to instruct the model how to handle different, in your case, temperature. But if there's like a common sense kind of correlation or between the temperature and what constitutes a good answer, then these foundation models might pick that up already. But it's a bit abstract here, so it's hard to tell what the final answer. But I would say that these models are fairly good at reasoning over also kind of metadata that you add to the system. So that we do for all the search results, for example. You have metadata of what MIME type it is and all of those things. And you can also there have, if you have a people graph in your company, you can have like you can encode which documents have been edited by people that you're likely to be working more closely with and so on. And that could be signals that you could include as well. And from what we see, these models from even the foundation models in a zero shot setting can often reason pretty well around those things as long as it's reasonably common types of attributes.
The last part got me thinking of whether, let's say, OpenAI, for example, and the 001 model, do you think it is currently able to like read my cookies and interpret me as an individual in this way so that it actually adjusts its answers based on who I am rather than the general mass? Because I can see this is the case in the profile and you choose to memorize different models like this.
Yeah, probably. I mean, not sure about how they do with the cookies, but from what I think is really exciting is also typically for recommendation systems, you used to look at also, you had like a matrix, for example, of entities to recommend and users, and you looked at how often did the user click on it, and then you condense that matrix to get like associate scores basically for recommendation.
Okay.
But I think that you can also really nicely compress user histories. For example, all their historical searches and what they did, you can encode that as text, and then you can use these kinds of models to compress that either as embeddings or as just a text description of the user, which is super interpretable, and the user can even edit it. So basically, the system could have a description of you that it's inferred, like this is who I think you are, based on what you have done, and then use that for recommendations, for getting better retrieval results and so on. But you could also edit it. So I think that's really, really cool to me. It's like, because usually you didn't have any way to control these systems. Once they had built a profile of you and started recommending things, really hard to get out of it, basically.
Right. I think that answer will have to wrap up this interesting discussion after this interesting talk. Thank you very much, Oscar, for this. Welcome back next week, everybody. We'll have Newton M.Y. Kenyan-Jui, who's a PhD candidate at Chalmers University of Technology, and he's going to visit us in person at our Gothenburg office at Lindholms Allén 10, and also available on Zoom, of course. So welcome back next week. Thank you for today.
Thank you.